So in 9.1, we have seen how to derive equations in terms of time and in terms of displacement. And in 9.2, we have learned how to sketch the graph for a simple harmonic motions. Okay, we have learned how to sketch a VT graph, AT graph, XT graph, and also the EX graph. So today we're going to see how to calculate the periods of simple harmonic motions if the angular frequency and the frequency are not given in the questions. Okay, now let us start from the simple pendulum. So if you look at this diagram, okay, the simple pendulums that we have, okay, you have a bob that's being hung by a string, and then this bob, you lift it up to a certain angles, but remember, angle should be less than 10 degree. Okay, angle should be less than 10 degree, so that you can assume the displacement is a straight line in the diagram. Okay, because when you lift it up, okay, the distance, the shorter distance between the equilibrium positions and the object actually is a slope, but if the angle is small enough, then you can ignore the slope. Okay, you can treat it as a straight line. So in this case, since the bob is being hung by strings, therefore it has a tension, and we know that every object comes with a weight, therefore it has a mg here pointing downwards. So if you look at this diagram, I have two forces. They are both pointing towards different directions. So I have to decide where is the x-axis and where is the y-axis. So I'm going to take the tangents of the circle as the x-axis. And I'm going to take the line that is collinear with the string as the y-axis. Meaning that I have to resolve the weight into x and y components. So if I resolve mg, I'm going to get mg sine theta on the x component and mg cos theta on the y component. Now, try to observe, try to go through this diagram again, and try to identify the force that causes the object to move back to its original positions, to its equilibrium positions. So based on this diagram, the force that causes the object to move back to its equilibrium position is a mg sine theta. Therefore, we call this restoring force. Okay, so the component tangential to the circular path mg sine theta is a restoring force, okay, which try to bring the object back to its equilibrium positions. So there are some misconceptions among students. Students always thought that restoring force is a force that is being stored in a spring, that exists only in a spring. In fact, it is not. Okay, restoring force can exist in any positions, as long as, okay, it can exist in any form, as long as it is a force that is trying to bring the object back to its equilibrium positions. So in this case, since I know that restoring force is mg sine theta, I can write it down as Fs equals to negative mg sine theta. Why negative? Because it is always opposite to the displacement. So now try to look at the diagram again. When you lift the object to the right hand side of the equilibrium position, this part is always a positive x. And whenever your object is located on the positive x side, the force, okay, the restoring force will always pointing to the left. Because restoring force is the force that is going back to the original positions, and original positions is located on the left hand side of the object. Okay, therefore restoring force is always a negative force. Okay, if you still remember, in a spring we have negative kx, right? So that negative, it has this meaning. Okay, it carries the same meaning. So negative, it is because it is oppositely directed to the displacement. So now that you have fx equals to a negative mg, well, let's recall, we assume that angle is less than 10 degree. Okay, now is the reason. Okay, I'll show you the reasons why we say it is 10 degree. So this is L, this is angle. If your angle is very large, then this x, we cannot assume it as a horizontal line. But now because our angle is less than 10 degree, it is very small. Therefore, we can treat this as a right angle triangles, okay, where this bottom line, the line at the bottom, is known as x. Okay, so based on these right angle triangles, we know that sine theta is equals to x over L. So substitute this sine theta into our restoring force equations. We are going to get Fs equals to negative mg bracket x over L. So this x over L is our sine theta. Okay. Now, let us apply Newton's second law in our situations. Why Newton's second law? Why not first law? First, because our object, it does not move with constant velocity. Okay. Second, because it does not stay at rest. And the most important thing is that our object is moving with an acceleration. So applying Newton's second law, we have summation F equals to ma. Now, what should we put on the left-hand side? What should we put as a net force here? Try to recall. What is the force that causes the object to move? Which force causes the object to move? The answer is restoring force. Therefore, I put restoring force on the left-hand side. So, based on our derivation just now, okay, we know that Fs equals to negative mg x over L. Okay, therefore you substitute into the equations and you are going to get negative mg x over L equals to ma. M and m cancel out. Rearrange the equations, you are going to get A equals to negative g over L x. Okay, so the reasons I put it in this form because I want to form a relationship for A and x. I want to see what is the relationship between these two variables. Now let's see what happens to g over L. G over L, the things that we know about G is always a constant value. It is equals to 9.81. And L, in our case, it is also a constant. Why? How can I say that it is constant? Because it is impossible for you to change the string while it is oscillating. Therefore, G over L, okay, G over L in our equations, it is a constant. Okay, we can combine these two things and just let it become a constant variable. So when you want to form a relationship between A and X, you can take out these constant variables and eventually you are going to get A is directly proportional to negative X. So based on the derivations, based on the definitions of simple harmonic motions, any motions that fulfill these conditions, okay, we say it is moving with simple harmonic motions. Therefore, we can say the motions of a simple pendulum exhibits a simple harmonic motions. Now, let's go back to our topic. In this subtopic, we want to derive the period. Okay, so what are we going to do? Again, we want to find a general equations that can be used to find the period. So we are going to apply A. Why? Because the general equations for A is A equals to negative omega squared x, and we have an omega here. Alright, so this is what we call general equations. So it can be used in any simple harmonic motions, not just for simple pendulum. The equations that we derived just now can only be used for simple pendulum. Okay, you cannot use it for spring. But these equations, you can use in any situation. That's why we call it general equations. And the most important part about this general equation is because it has a omega here. So this omega is very important. Why? Because we have learned this before. Omega, frequency, and period, they are one family. Okay? So you compare the equations that we derive with the general equations, you'll find that omega squared is equals to G over L. Rearrange the equations, you're going to get omega equals to square root G over L. So now we want to derive the equations for period, right? Therefore, we use omega equals to 2 pi over t. Rearrange the equations, you have t equals to 2 pi over omega. So when you put omega, okay, when you put square root G over L into our equations here, you are going to get 2 pi square root L over G. Okay, you have to flip the equations if you want to move it from denominator up to a numbers. Okay, so this is a equations for simple pendulum. Okay, you can only use it for simple pendulum. Yeah, remember these equations you cannot use it for spring. You can use it for simple pendulum only. So in order for the simple pendulums to execute simple harmonic motions, there are three conditions. Alright, okay, so the conditions for simple pendulums execute simple harmonic motions. First, we say just now, the angle has to be small. Okay, it has to be small. Usually we take it less than 10 degrees. And the string has to be inelastic and light. Inelastic means, like, for example, you cannot use rubber. Okay, if you use rubber, then the length is not constant, so you cannot derive the equations. And has to be light. Okay, so the mass, it doesn't contribute towards the restoring force. Okay, it doesn't affect our calculations. And the last one, only gravitational force and tensions in the string. So we assume there's no air resistance. We assume we carry out this experiment in an ideal situation, in a closed system, okay, where there's no any other external factor that can affect the motions of the simple pendulum. Now let's look at the period for a spring mass system. Okay, let's consider a horizontal spring mass system first. So if you have a horizontal spring mass system, this is how it looks like. So you attach the object to a spring, okay, at the beginning it might oscillate a few times, and then at the point where it comes to rest, okay, where it comes to rest, this is what we call equilibrium positions. Okay, and this is the point where we take x as 0. So before you start the derivations, before you do the derivations, there's one very important assumption that you must make, which is the surface is always smooth. Okay, if the surface is not smooth, if there is a frictional force in between the object and the surface, then the derivations will become much more complicated. So to make it easier, we always assume the surface is smooth. Alright, so as you can see, assumes that the object is oscillating on frictionless surface, frictionless, the smooth surface. So the only force acting on the object is the restoring force of the spring. So what does it mean? Okay, if you push the object towards the positive x, okay, the force that trying to push the object, trying to bring the object back to its original position, is the energy stored in the spring. So this is what we call restoring force. And as you can see here, when I have positive x, my F is always heading to the left, which gives you a negative value. Okay, so if you compress a spring, if you push this object to the left, meaning that you push the object towards a negative displacement, the restoring force is always heading to the right. Okay, it's trying to push the object back to its original positions, and the original positions is located on the right hand side. Therefore, your F is a positive value because it's pointing to the right. Okay, so this is the restoring force in the spring. So F equals to Kx. Okay, this is according to the Hooke's law. This is according to what you have learned in a secondary school. And this Kx, the reasons why we have a negative here is because it is always opposite to the displacement. So now that we know that restoring force is equal to negative Kx, and we know that our object is moving with an acceleration, let's apply Newton's second law again. So according to Newton's second law, we have summations F equals to ma. We're going to repeat the same step. We substitute restoring force on the left hand side. Therefore, we have negative Kx equals to ma. You rearrange the equations, you're going to get negative K over mx. Okay, A equals to negative K over mx. Again, we want to see what is the relationship between A and x. So now let us see what is the K and m. What can we say about K and m? K obviously is a constant. Why? Because it is known as spring constant. So it depends on the types of the springs that you are using. So it is impossible that you change the springs while it is oscillating, right? So spring constant is a fixed value. Then how about the object m? M is also constant. Why? Again, it is impossible for you to change the object while it is oscillating. Therefore, in this case, we can combine these two and make it just a simple constant variable. Okay, so two of them, they are constant. Okay, now, after we identify the constant variables in our equations, we can then form a relationship for it. So, if you form a relationship based on the equations, you're going to get A is directly proportional to negative x. So again, based on this relationship, it tells us that the horizontal spring oscillations is a form of simple harmonic motions. So it's moving in simple harmonic motions. Then how are we going to derive the period for a horizontal spring oscillations? Well, same. Let's go back to the general equations. A equals to negative omega squared x. Okay, so this is once again our general equations. Always keep that in your mind. these general equations can be used for any simple harmonic motions, but the equations that we derived just now can only be used when it comes to a spring, when it involves a spring. So based on the comparisons, you get omega square equals to k over m. Rearrange the equations, you're going to get omega equals to square root k over m. So try to recall. Omega equals to 2 pi over t. You rearrange the equations, you're going to get t equals to 2 pi over omega. And then again, you substitute this one into the equations. Eventually, you're going to get 2 pi square root m over k. So remember, this one can only be used for spring. Okay, can only be used in a spring. If you have a simple pendulum, then you cannot use these equations. Alright, so don't mix up. Make sure you select the correct equations for the correct system, according to its system. See whether it is a simple pendulum or it involves a spring. Okay, now let's see what if the questions involve a vertical spring. Okay, let's look at these 3 diagrams. You have diagram A, diagram B, diagram C. Why 3 diagrams? Because you need to determine the extension. So initially you have a spring without any objects. So this is the initial positions, okay, the spring without being stretched. And the diagram B is after you attach an object to it. So at positions B, okay, this is when the object comes to equilibrium. Okay, so the reasons why we add in this step is so that we can simplify our equations after this. Okay, you can straight away proceed to questions diagram C, but then the equations will look much more complicated. So if you add in one diagram, okay, you consider one more situations, then you will be able to simplify the equations after this. Alright, now after you attach an object to the springs, okay, it might oscillate a few times, and when it comes to rest, then this is why we call it equilibrium positions. So from here, we will be able to determine the restoring force inside the spring. Okay, we can determine the restoring force inside the spring. And this is when the object is not moving. So you cannot determine the relationship between A and X by using diagram B. Therefore, you add in one more diagram, you call it diagram C. So in diagram C, you push the object to the negative displacement part, okay, because it is the positions below the original position. So it is a negative displacement. So as you can see here, the restoring force is trying to push it back up. Okay, so you have a restoring force going upwards, and then you have an mg going down. Okay, now let's see how are we going to simplify the equations. So a free light spring with a spring constant hung vertically as shown in figure A. Okay, so we have a spring constant K, and then remember when it comes to spring, the restoring force for spring F is always equals to negative Kx. Okay. So an object of mass m is being tied to the lower end of a spring as shown in figure B. So when the object achieves equilibrium position, so when it comes to equilibrium positions, what can we say about the object? The object is fulfills the conditions in the Newton's first law. So we have summations F equals to 0. So based on the diagram, what do we have? We have a restoring force going upwards, and then we have a weight going down. Okay, restoring force going up, weight going down. And we know that restoring force is equal to negative Kx. Therefore, we can write our equations as Fs minus mg equals to 0 and negative Kx naught. Okay, why Kx naught? Because we have two times extensions. So for the first times we use x naught, the second times we use x. So make sure to put a subscript here to distinguish whether this x belongs to the first diagram or belongs to the second diagram. So negative Kx naught minus mg equals to 0. Rearrange the equations, you get negative Kx naught equals to mg. So this is the equations that come from diagram B. Now let's see how to form another equation for diagram C, where your object is moving with an acceleration. So when you push the object downwards, what is going to happen? Okay, now let's see. The object is then pulled downwards to a distance x. Okay, and released as shown in figure C. So according to figure C, once again, we have an object like this. So restoring force going up, and then mg going down. And now my object is moving with an acceleration. Therefore, I have summations F equals to ma. I'm going to apply Newton's second law now. Okay, so my A is heading up. And therefore, I have Fs minus mg equals to ma. So what should I put as Fs? Now, if we want to apply Fs, we know that Fs is equals to kx. But now your object is being pulled twice. Okay, once when it's at its equilibrium position, and the second time is when it is at its maximum position. Therefore, for the third case, our Fs is equals to kx naught plus x. This extension is based on the original length of the spring. Okay, and also in our previous previous slide, okay, in our diagram B, we know that negative kx naught is equals to mg. So we are going to include these two equations. We are going to substitute these two relationships into our equations here. Therefore, you can get negative, okay, it's a negative, I missed a negative here. So it's a negative kx naught plus x minus negative kx equals to ma. You simplify the equations, you're going to get a equals to negative k over mx. It is exactly the same as the equations that you obtained in your horizontal spring. So we know that a is directly proportional to negative x. Therefore, we can say vertical springs, oscillations, it also exhibits the simple harmonic motions. Okay, it is also a form of simple harmonic motions. So basically what I'm going to do next, repeat the same thing, compare with the general equation, a equals to negative omega x. Remember, this is general equations that can be used in any situations. So rearrange the equations, okay, compare, rearrange, and eventually you are going to get the same t. T equals to 2 pi square root m over k. So this is an equation that can be used for horizontal or vertical. Okay, as long as it is spring, then you can use it. It doesn't matter whether it is a horizontal spring system or a vertical spring system. Alright, so just now we have three conditions for a simple pendulum, right? So how about spring? Same, okay, we also have three conditions in order for a spring mass system to execute simple harmonic motions. So the first one, the elastic limit of the spring is not exceeded. Why? Because when it is being exceeded, then the x cannot be used anymore. Okay, it won't go back to its equilibrium positions, to its original positions. The second is the spring is light. We assume it's massless and it obeys Hooke's law. And the last one, once again, we assume the surface is smooth when it comes to horizontal spring, and we assume there's no air resistance at all. Okay, so that's all for 9.3 and that's all for chapter 9. If you have any questions, you may ask in the class.